Hello, I'm Santiago Mol Lopez, and in this video about derivatives, we will be applying the chain rule to primarily compute derivatives of the exponential and logarithmic functions. The requirements for this video are a basic understanding of the derivatives of elementary functions. However, I will also review the derivatives of the functions as they appear during the video. Let's begin by examining some derivatives using the chain rule. What to do if asked to calculate the derivative of e to the power of g of x? You should be aware that there's a rule for this, which is as follows. E to the power of g of x is equal to the same function multiplied by the derivative of the exponent. It is very important to know all this. What happens if instead of the number e, I put here a number a in general? The derivative will be nearly identical. If you notice the similarity, the initial function remains unchanged. The derivative of the exponent is added, but in this case, you also need to include the natural logarithm of the base. What should we do if someone asks us to find the derivative of the logarithm of a specific function? It's clear that we should know the derivative of the natural logarithm of x, which is 1 over x. But what if there's no x involved? What if it's the natural logarithm of something else or a more complex expression? In such cases, the derivative is 1 divided by g of x, where g of x represents the function within the parentheses, multiplied by its derivative. Note that this derivative is not in the denominator, it appears in the numerator. Let's generalize this example. What if someone requests the derivative of the logarithm with base a of g of x? In this case, we essentially apply the same rule, but as before, we include a natural logarithm of a in the formula. Previously we multiplied, but in this case we add in the denominator. Therefore, the derivative would be 1 over the natural logarithm of a multiplied by g of x, which is the function within the parentheses without differentiation, and then multiplied by the derivative of g of x. Let's see examples with each of these rules. We will start with the function e raised to the power of a certain function g of x. As we've just discussed, its derivative would be e raised to the power of g of x times the derivative of g of x. Remember, the function raised to the power of g of x remains as it is, and then we multiply it by the derivative of the exponent. Let's consider what happens when we are asked to calculate e raised to the power of x squared plus x plus 1. I've used parentheses here to emphasize that everything is in the exponent, although they are not necessary. What is the derivative of this function? The first step is to identify the components. Clearly, the number e remains the same in both cases, and the function g of x in this instance is x squared plus x plus 1. We apply the rule, and then I would copy the function as it is, as shown here, and multiply by the derivative of the exponent. What is the derivative of the exponent? We have a polynomial, x squared plus x plus 1. Let's review how to calculate its derivative. When we have functions of the form x raised to a power, the derivative follows this pattern. The exponent comes down in front, and then we subtract 1 from the original exponent. In this case, that 2 comes forward, as you can see here, resulting in 2 times x. Now, the exponent that used to be 2 becomes 2 minus 1, which is 1, and we don't write it explicitly. The next derivative is for x, which is 1, and the derivative of a constant is 0. So, the expression here, 2x plus 1, represents the derivative of x squared plus x plus 1. It's important to note that the 1 in this expression comes from the derivative of x, and the derivative of a constant like 1 is indeed 0. Keep that in mind. Let's now see another example. E raised to the power of sine of x. In this case, if we identify it as before, g of x would be the sine of x. How do we find the derivative of this? The key consideration here is that the derivative of the sine of x is the cosine of x. Let's apply the formula. When we do so, you'll notice that the derivative of e raised to the power of sine of x remains exactly the same, as I've copied here multiplied by the derivative of the sine, which would be the cosine of x. Let's generalize this. What if I have functions of the form a raised to the power of g of x? As we mentioned earlier, the derivative is quite similar to that of e raised to the power of g of x with the addition of the natural logarithm of a. So, the derivative of a raised to the power of g of x remains equal, times the natural logarithm of a times g of x, derivative of the exponent. Let's see some examples. It's quite similar to what we've seen before, but this time, instead of the number e, we have the number 2. What is the derivative of 2 raised to the power of x cubed plus x squared plus 1? Let's apply the rule. In this case, a is equal to 2. As you can see, the base is 2, and g of x is the polynomial that's in the exponent. Its derivative is to precisely copy the polynomial and then multiply it by the natural logarithm of a. But in this case, the natural logarithm of a is the logarithm of 2 because the base is 2. We multiply this by the derivative of the exponent. After recalling what we discussed a while ago about the derivatives of power functions, this should be an easy process. We'll take it step by step. For x cubed, the derivative is 3x squared. The 3 comes down in front, and we subtract 1 from the exponent, as shown here. Next, what is the derivative of x squared? The 2 comes down in front, and as mentioned earlier, 2 minus 1 in the exponent results in 1. As for the derivative of 1, which is a constant term, it is 0, so it doesn't need to be included in the result. This serves as an example for the derivative of a function in the form a raised to the power of g of x. Let's consider another example. 7 raised to the square root of x. Notice that in this case, a is 7, and g of x is the square root of x. Before proceeding, it's crucial to review what the derivative of the square root of x is. The derivative can be deduced knowing that the square root of x is x raised to the power of 1/2. Deriving x raised to a power involves bringing down the exponent and subtracting 1 from it. Considering that the square root of x appears frequently, I recommend memorizing its derivative for efficiency. The derivative of the root of x is 1 over 2 times the root of x. With this knowledge and this rule, we can now calculate the derivative. In this case, it would be 7 raised to the square root of x, which remains unchanged, multiplied by the natural logarithm of 7, the base, and further multiplied by the derivative of the exponent. What is the derivative of the square root of x? It is 1 over 2 times the square root of x. Now let's consider the example of the natural logarithm of a certain function, g of x. Recall that the derivative of the natural logarithm of x is 1 over x. In this case, it is 1 over g of x multiplied by g of x. The function that's within the parentheses moves down to the denominator without any differentiation. It's crucial not to alter this function in this case. Then you multiply it by the derivative of g of x. An example. The natural logarithm of x raised to the power of 10 plus x squared. What is its derivative? First, let's identify. G of x in this case is x raised to the power of 10 plus x squared. How do we find its derivative? We apply the rule. We take the function that was within the parentheses and place it in the denominator. Then we multiply it by the derivative of that function. The derivative of x raised to the power of 10 is 10 times x raised to the power of 9, as the exponent comes down, and we subtract 1 from the exponent. Additionally, we have the derivative of x squared, which is 2x. We now have the derivative of the natural logarithm of x raised to the power of 10 plus x squared. An example involving a mixture of the logarithmic function and the trigonometric function sin of x. How do we differentiate this? We begin by identifying the components. G of x is the sine of x. By applying the rule, the derivative would be 1 divided by the sine of x, which is the same function you see in the denominator. Now we multiply by the derivative of the sine of x, which you should all remember is the cosine of x. What happens when I apply the rule of the logarithm to the base a of g of x? Remember that the derivative is 1 divided by g of x, multiplied by the natural logarithm of a times g prime of x. Let's consider an example. The logarithm to the base 2 of 5x to the 4th. What do we need to identify here? We see that a is 2 and g of x is 5x to the 4th. We can apply the formula as follows. The expression inside the parentheses becomes the denominator. We then multiply it by the natural logarithm of the base, which in this case is 2. And finally, we multiply it by the derivative of what was inside the parentheses. Do you see it? 5x to the 4th. In this case, there's an element that might seem a bit unusual, which is the constant 5. So, how do we differentiate 5x to the 4th? You should remember that any constant that multiplies a function of x, like in this case, remains exactly the same. So the 5 remains unchanged. And what's the derivative of x to the 4th? The derivative of x to the 4th would be 4x cubed. The 4 comes down, and we subtract 1 from the exponent. But of course, since 5 times 4 is 20, that's where the 20 comes from. Let's see another example. The logarithm to the base 10 of the square root of x. We identify a, which is equal to 10 and g of x is the square root of x. Therefore, its derivative applying this rule would be 1 over the square root of x. The function that is here goes directly to the denominator, multiplied by the natural logarithm of the base, times 1 over 2 times the square root of x. Where does this come from? It is simply the derivative of the square root of x. Today we've covered the calculation of derivative functions involving exponentials and logarithms. I hope this has been helpful. Thank you very much for your attention.